You know, when you see a drone slicing through the sky, have you ever stopped to think about what's really keeping it up there? It's not just the propellers, not just the pilot's skill. It's this invisible, high-stakes conversation happening hundreds of times a second. Today, we're going to pull back the curtain on the unseen world of RF engineering, the lifeline that keeps a drone from becoming, well, a very expensive piece of falling plastic. All right, let's get into it.
So, let me ask you a quick question. What do you think is the single most vital component on a drone? You might think it's the powerful motors, right? Or maybe that high-res camera? The battery, for sure, that's got to be up there. All totally reasonable guesses, but the real answer? It's something you can't even see.
The answer is the radio link. And the person responsible for that link is the radio frequency, or RF engineer. I mean, just look at a real-world job description like this. They are the architects of the drone's entire connection to the outside world. They design it, they test it, they make sure it's bulletproof. Without them, there's no control, no video, there's no mission.
So here's our game plan. First, we'll look at the two different communication links every drone absolutely has to have. Then we'll break down the hardware that makes it all work, the RF chain. After that, we'll dive into the invisible enemies that engineers are constantly battling. And finally, we'll see how they take a design from paper all the way to flight.
First up, the two critical links. Because you see, not all radio signals leaving a drone are created equal. They serve two very different but equally vital purposes.
On one side, you've got the control and telemetry link. Just think of this as the drone's nervous system. It carries the pilot's commands to the drone and brings critical data, like battery level and GPS location, back. This link has to be ultra-reliable. It's low data, low latency, but if this connection drops, game over. You lose the drone, period. Then you have the video downlink. This is a whole different beast. It's all about bandwidth, shoving a high-quality video stream back to the pilot. Yeah, low latency is important so you can fly, but a few dropped frames here and there, a little bit of static, it's not the end of the world like losing the control link is.
And to meet these totally different needs, engineers have to make a really fundamental trade-off with the frequencies they use. For that rock-solid control link, they almost always go for sub-gigahertz frequencies, like 915 megahertz. These lower frequency waves are like a bass note. They travel farther and can punch right through obstacles like trees and buildings. For video, though, they need that bandwidth, so they jump up to 2.4 or 5.8 gigahertz. This gives them a huge data pipe for beautiful video, but the trade-off is pretty clear: shorter range and a signal that gets blocked much more easily.
So how does this all actually happen on the circuit board? Let's peel back the layers and look at the anatomy of an RF chain. These are the actual hardware building blocks that make these invisible links possible.
So on the transmit side, it's a fascinating journey. It all starts with simple digital data, a 1 or a 0. A modulator then cleverly encodes that data onto a basic radio wave. A mixer kicks it up to the right transmission frequency, say 915 megahertz. A filter cleans up any junk noise. And then comes the muscle, the power amplifier, or PA. This is the component that gives the signal the shout it needs to travel for miles before the antenna finally launches it into the air.
Now, the receiver has to do the exact opposite, and its job is way harder. The antenna catches a signal that is now just an incredibly faint whisper. A filter immediately chops out any interference from other frequencies. And then comes the absolute hero component of the receiver, the low noise amplifier, or LNA. Its one job is to take that tiny, weak signal and boost it, but, and this is the key, without adding much noise of its own. After that, the rest of the chain can decode the data. But everything, and I mean everything, hinges on that LNA hearing that whisper in the first place.
Let's just focus on that LNA for a second, because it is just a perfect piece of RF engineering. It's the very first active component the signal hits, and you'll always find it physically as close to the antenna as possible. So why is that? Well, you want to amplify that precious signal before it gets any weaker traveling down a cable, and before any other noisy electronics on the board can contaminate it. A good LNA is literally the difference between clear reception and just a wall of static. It's the heart of a receiver sensitivity.
Okay, so you can build the most elegant hardware chain in the world, but that's only half the story. An RF engineer's real job is to make sure that link can survive out there in the messy, noisy, unpredictable real world. They are constantly fighting these invisible enemies: signal loss over distance, interference from every Wi-Fi router and cell phone, and sometimes even intentional jamming.
And their number one weapon in this fight is something called the link budget. You can honestly just think of it like an accountant's spreadsheet, but for radio signals. It's this super careful accounting of every single thing that boosts the signal,
those are your gains, and every single thing that weakens it, those are your losses. It is the fundamental calculation they use to predict, on paper, whether a link is actually going to work.
And this table just lays it out perfectly. Engineers start with their transmit power. That's their starting capital, right? They add the gains from both antennas. Then come the expenses. They subtract losses from little things like cables. And then they subtract the big one, path loss. That's just the unavoidable cost of physics, of sending a signal over a certain distance. At the end, they look at the bottom line, the received power. And the big question is there enough left in the bank for the receiver to hear it? In this case, yeah, we're in the clear.
But here's a piece of wisdom from the pros. You never, ever design for the bare minimum. Experienced engineers live by this rule. You always add a safety buffer, what's called a fade margin. It's an extra 10 to 20 decibels of power you budget for just to handle all the unpredictable stuff. A badly aimed antenna, weird weather, unexpected interference. It's the cushion that makes a link reliable in the field, not just in the lab.
Another really clever defense they use is a technique called spread spectrum. Instead of putting all their eggs in one basket on one single frequency, the system spreads the signal out over a much wider range. The most common way to do this is frequency hopping, where the transmitter and receiver are constantly jumping between dozens of different frequencies in a random-looking pattern. This makes the link incredibly tough. A jammer might knock out one or two channels, but who cares? The link just hops to a clean one in a millisecond.
So, after all the math, all the calculations, all the defensive designs, comes the moment of truth. This is where engineers have to prove it all actually works, moving from the theory on the whiteboard to an actual drone on the launch pad.
And they do this with an extremely rigorous pre-flight checklist. They hook up specialized equipment to make sure the antenna is perfectly matched so no power gets wasted. They measure the transmitter output to make sure it's actually putting out the power they planned for. They use a spectrum analyzer to make sure the signal is clean and legal. And of course, the big one, they take it out in the field and fly it farther and farther away, logging the data to find the absolute breaking point of the link.
But here's the final, crucial gotcha that trips up so many people. You can have the most perfectly designed radio link in the world, and your drone can still fall out of the sky. Why? Because of its own noise. All the motors, the power supplies, the digital chips, they're all screaming with electromagnetic interference, or EMI. If that noise isn't managed, it's like trying to have a whispered conversation right next to a jet engine. Your receiver will be completely deafened. The system as a whole has to be designed to be quiet.
And that really brings us to the big picture. This whole deep dive into drone communications, it's really a window into our future. As we build a world of autonomous cars, remote robotic surgery, and a planet where everything is connected, all of it, every last bit, relies on these invisible wireless lifelines. So the question we're left with isn't just for engineers, it's for all of us. As we rely on them more and more, how will we ensure these lifelines can be trusted to never, ever break?